Simplifying series parallel circuits is proven to be a difficult task for some. In this video, I will be providing not one, but two methods of simplifying resistors in a combined series parallel circuit. But before that, let's not forget how to solve for equivalent resistance for resistors in series circuit or in parallel circuit, as well as the voltage source and the total current running through the circuit. By now, we should know the relationship between voltage, current, and resistance, which is voltage is equal to current times the resistance. The first method to solve a series parallel circuit is just to simplify the circuit and turn the circuit to just a series circuit. Well, that is easier said than done, so some complex circuits like this might be difficult to simplify. Another way to simplify complex circuits is by using the arc method. Yep, that method is a made-up name because I have no idea how to call it. I name it that way because, well, that's me. But in a serious note, I call it arc method because it requires you to analyze the circuit, redraw it, and finally compute or calculate whatever quantity you are asked to solve. Maybe you have seen this method before or some teachers are using it. I just don't know. But for this video, I will just call it the arc method. I can demonstrate these methods by applying it in an example. Let's try this one. Find the equivalent resistance and the current through the voltage source of the circuit. The values of the resistors are given below. This problem is not that difficult, so before applying the arc method, let's try the regular one and let's compare the answers later on. So we are asked to solve for the equivalent resistance and the total current running through the circuit. To simplify this, we look at resistor 4, 6, and 5. As you can see, they are connected in series. So to solve for the equivalent resistance of these three, we add their values together. So resistors 4, 6, and 5 is equal to 15 ohms. Next is to draw the simplified version of the circuit where we can see that resistors 4, 6, and 5 are already combined. This will show us as well that R3 is connected in parallel with R4, 6, and 5. So if we simplify R3 and R4, 6, and 5, we will get a value of 2.5 ohms. After drawing again the simplified version of the circuit, now that we combined R3, 4, 6, and 5, we notice that we have a series connection between the two remaining resistors R1 and R2 and the combined R3, 4, 6, and 5. So to simplify them further, we just need to add their values, which finally will give us the equivalent resistance of the 6 resistors. The equivalent resistance is equal to 5.5 ohms. Now, to find the total current running through the circuit, we will use the relationship between the voltage source, the total current, and the equivalent resistance. Therefore, we can say that I total is equal to the voltage source divided by the equivalent resistance. The I total now is equal to 1.82 amperes. Now let's try to compare our answer if we will use the arc method. To analyze the circuit, we need to trace the path of the current. We also need to identify the junctions in the circuit. These junctions are where the current will split or meet in the circuit. In this example, there are two junctions, junction A and B. Next step is to redraw the circuit. The first thing to draw is a straight broken line which represents the path of the current. We start from the positive terminal of the voltage source. We see that the current will run through R1 before it will encounter the first junction, junction A. At junction A, the current will split into two. The first split will run through R4 and the second split will run through R3. We leave R3 for the meantime and let's continue with the first split. We notice that before it will reach junction B, the current will run through R6 and R5. Junction B has two other connections. The first one will run through R2 before it will go back to the negative terminal of the voltage source. The second split is actually connected to resistor 3, so we will connect these two together. So that ends our redrawing step. This illustration will tell us a lot of things, one of which is that resistors 4, 6, and 5 are connected in series. So, our computation step starts from here. R4, 6, and 5 is equal to 15 ohms because they are connected in series. From the illustration also, we can clearly see that R4, 6, and 5 is connected in parallel with R3. So simplifying that will give us a total of 2.5 ohms for R4, 6, 5, and R3 since they are connected in parallel. You don't need to redraw again, especially if you have a good imagination, but I will just draw it so I can explain this properly. In your new illustration, the current starts in positive terminal of the voltage source, going through R1 and now to resistors 4, 6, 5, 3 and to resistors 2 before returning to the voltage source. Your main objective in doing arc method is to end up with a straight line because this will tell us that we have resistors in series already. Finally, adding these values will give us the equivalent resistance of all the resistors, which is equal to 5.5 ohms. Now, solving for I total will give us 1.82 amperes. These results are the same using the first method I used a while ago, so you can use either of the two depending on your preference. For sure, the first method will solve a lot of series parallel circuits problem, while the arc method is very effective with more complex circuits. Let's try another one. In this example, I will be just using arc method as our way of practicing. Again, we are asked to solve for the equivalent resistance as well as the total current. The resistors are given below. Analyzing this circuit will tell us that there are 3 junctions with several splits. Again, this broken line represents the path of the current, and our main job here is to make sure that we will end up with a straight line after simplifying the connections. We start from the positive terminal of our voltage, going to R1 before encountering our first junction, junction A. There are 3 splits here, first going to R4, second to R7, and third to R3. We leave R7 and R3 for the meantime and we will follow the first split. From R4, the current will run through R6 before it will encounter another junction, junction B. In this junction, we have another 2 connections. One is towards R5 and the other one is actually connected to R7. After that, we will meet another junction again. And from this junction, junction C, we have a connection that will run through R2 before it will go back to the negative terminal of our voltage source. Also at junction C, the other connection is actually towards R3, so we will adjust our drawing to accommodate this connection. And finally, we are ready to simplify this circuit. From the illustration, we can see that R4 and R6 are connected in series, and these two also are connected in parallel with R7. We will get 10 ohms from adding R4 and R6, and we will get 4.12 ohms after simplifying R4, 6 and R7 since they are connected in parallel. Now you can redraw again the illustration if you want, so you can have a better view of the simplified circuit. We can already flatten R4, 6, and 7 as well as R5 and R2. You notice that R4, 6, and 7 and R5 is connected in series. And they are also connected with R3 in parallel connection. Therefore, you can simplify that further. You will get 9.12 ohms from adding R4, 6, and 7 and R5. And you will get 2.26 ohms from simplifying R4, 6, 7, 5, and R3 since they are connected in parallel. Finally, we have the straight line that we are aiming for. So this means that our equivalent resistance is equal to 5.26 ohms by adding R1, R4, 6, 7, 5, 3, and R2 together. The I total will be 19.01 amperes. I hope you are getting used to it, but if not, you can always try the regular one. Try to simplify this circuit as well using any method and comment the values of equivalent resistance and total current in the comment section below. And let's compare our answers later on. That's it for me today. Have a good day and keep solving.